We're going to continue on here, wrap up chapter 9, get into some chapter 10. I think last time we talked about really kind of liquid state. We also talked about phases a little bit more, the 6 sort of phases or transitions of phases, not really 6 phases, but 3 phases, solid, liquid, and gas, with the 6 conversions, which obviously are melting. We got freezing. We have evaporation and vaporization, condensation, sublimation, and deposition. We also saw last time phase diagrams, which have sort of the pressure temperature components of substances, and they have a couple of lines that sort of look sometimes like this, and usually we have our solid sort of phase, our liquid, and our gas phase, and a couple of points along this which are sort of important. We do have our triple point, which is right there. That is really the sort of pressure temperature combination where all 3 phases basically are happening at the same time. We also have typically off of this line, drop that way a little bit more. That's our critical point, where we have our critical temperature, critical pressure, and beyond that point, supercritical fluid is where we have it, and that's where it has some properties. Obviously, it flows sort of looks like a liquid, but also has properties of gas as they sort of run into each other as well. Remember the transitions as we kind of go across phases and these lines. And again, obviously, that would be melting, freezing, evaporation, condensation, sublimation, deposition happening there. Also, as we talked about, if you kind of hit the line there, you do have obviously both phases happening at the same time. Really under standard conditions, that's a pressure of 1 atmosphere. So again, if you sort of draw a line across that 1 atmosphere and come down from those lines where it changes phases, that'll give you kind of your normal freezing point and boiling point for that particular substance. Any questions on any of that there? All right, so we're going to finish up this chapter talking just a little bit about solids and a couple of aspects of solids and some different types and what's going on. Solids obviously are rigid. They cannot transmit pressure in all directions. There's a couple of different types of solids that we come across. There's crystalline solid, which is these really ordered arrangement of particles. So like ionic compounds oftentimes are crystalline solids. These are arrangements of particles when they are in the solid in a very ordered, repeatable sort of pattern that happens. An amorphous solid has very little long-range order, and has a definite shape and are hard. Things like glass and organic polymers are more amorphous sort of solid. We're going to focus on really sort of crystalline solids here. And within that, we usually will have what's sometimes referred to as a crystal lattice. And when we allow something to cool slowly from the liquid phase, everybody will sort of lock themselves in, as we've been talking about. Obviously, they're going to sort of lock themselves in a way that will maximize the attractive forces and minimize the repulsion type forces. The idea there is really as they sort of slow down and move in as close as they can and kind of move around to maximize those attractive forces. They're also minimizing the energy associated with that sort of compound. And that is really the goal of a lot of things in chemistry, is to get things to a sort of lower energy sort of situation, which is, again, a more stable situation. The result is we do get this crystalline solid, and the arrangement of these particles is what's known as the crystal lattice. And there is such a repeatable pattern when this occurs that you could really take like a snapshot of the solid, just like a little square of the solid, and you could use that square, basically just repeat it, just keep putting that square next to each other, and you can rebuild the entire structure. So that's sort of how repeatable it is. when you grab sort of a small unit of it is what's sometimes referred to as a unit cell. So for example, if we had the arrangement of a solid particle such as this in a non-three-dimensional drawing, and if we were to choose a unit cell, for example, sometimes people might think in this situation, well, if each of these represents an atom, I probably want to choose a unit cell like this, and I'll just choose an atom as a unit cell by itself. The problem with doing that, if you sort of choose that as your unit cell, is although you may have the entire atom there, you have no sort of information about how it relates to all the other atoms that are next to it. So that would not be the best choice, for example, to choose to use for a unit cell. Now, for example, if I sort of took a little bit of everybody here, hold on a sec here. So if I took everybody here and a little piece of everybody, the benefit of doing that is, although I don't have an entire sort of atom, I do have relationship of how everybody is sort of stacked up next to each other. So if I take this guy and just repeat that pattern, drop me a little unit cell there on the bottom. And now, as you can see, it's much easier to recreate for the three-dimensional structure of the solid. Again, using this, you really don't have any relationship of how this guy is sort of connected to others. So oftentimes when we choose a unit cell, we want a little bit of everybody neighboring sort of atoms. That way, when we use it to rebuild our structure, we have that sort of relationship of how far everybody is, to one another. Now, when we look at unit cells, it's a three-dimensional, usually containing 2 to 3 layers of particles. And again, it gives us a lot of information about the neighbors and so forth. So for example, here in this one, they chose a unit cell where they do have a whole atom in the middle and a little bit of corners of atoms to give sort of the relationship of where that guy is associated so that they can, again, just kind of rebuild the entire sort of structure. And again, you can see if you just take that, you can just keep rebuilding and you'll have the entire sort of three-dimensional structure. So each particle unit cell is supposed to know the lattice points, and these are connecting equivalent points throughout the sort of crystal lattice, which again helps you sort of see that repeatable pattern. There's a lot of different types of unit cells, and really for us, we're just going to look at cubic sort of unit cells, where sort of all the angles are 90 degrees. So another sort of relationship is, in terms of this, is what is referred to as the coordination number. The coordination number is really the number of particles that are in contact with each other, and that's the coordination number. For ions, it is the number of oppositely charged ions that are in contact with it. The higher the coordination number, the more interaction. Therefore, the stronger the attractive force is within the crystal lattice. Again, the only way that everybody can kind of get in contact with each other is they're attracted to each other pretty tightly and very close to one another in that solid sort of structure. Packing efficiency, which we're not getting too much into, is the percentage of volume in the unit cell that's occupied by particles. The higher the coordination number, usually you have a more efficient packing of those particles together, again, because everybody is sort of a lot closer to one another. So when we look at cubic unit cells, which is what we're going to mainly focus in on here, a couple of things. They all have 90-degree angles at the corners. The length of all the edges are equal. And if a unit cell is made of a spherical particle, 1/8 of the corner will be within the cube. If it's on the face of the cube of your unit cell, it'll have half of a particle. And if it's at the edge, is within it, you'll have a quarter of a particle that's happening. For the most part, the volume of a sphere is 4/3 pi r cubed. I would say most of the time, though, since we're using cubic here, that's going to be the one of how we're going to figure out the volume of it. It's basically the length cubed is very equivalent to like when you take obviously the length times the width times the height, right? And you get Again, if these were all in centimeters, you get cubic centimeters, which is a volume, right? So that's the idea here when we do this. So let's talk about a few of these type of cubic cells. The first type is what is referred to as a simple cubic, and sometimes abbreviated as SC. And we're gonna go through each of these in just a second individually, but it has basically one total atom per unit cell. Basically, it has an eighth of an atom in each of the corners. It has a coordination number of 6. And to calculate the edge length, it is 2 times the radius. So that is 2 times the radius. The next one is body-centered cubic, which is BCC. And sometimes the abbreviation for that. And that has actually 2 atoms per unit cell. And it has a coordination number of 8 because we have an extra atom sort of in the middle. And it is 4r divided by the square root of 3 is the edge length. And then we have face-centered cubic, which is sometimes abbreviated as FCC. And this has 4 total atoms. And it's basically 2 times r square root of 2, basically, is the edge length. So these are the 3 different types of cubic cells we're going to talk about here. And again, kind of the important relationships as we go through this. Simple cubic has 1 atom, body-centered has 2 atoms, face-centered has 4 atoms, and how to calculate the length is really important as well to do these sort of calculations. So let's take a look at first the simple cubic. As I mentioned before, the simple cubic has basically a eighth of an atom in each of the corners of the cube. And since there is 1, 2, 3, 4, 5, 6, 7, and 8 corners, 1/8 times 8 gives you 1 whole atom, basically. That's basically developed here in this unit cell. So if you have a simple cubic, it has a total, as I mentioned, of importance here of 1 whole atom. Again, basically in the corners of the unit cell. And again, the radius is basically 2 times the radius is the edge length here of this cubic cell. And that's what we can see here. Again, you got kind of it dissects out the corners right here. And again, we got that eighth of an atom basically in each of these corners to give you 1 whole atom when it's all said and done. It also obviously, when we're talking about the edge length, we're talking about, again, the edge of the cube there, and that is 2 times the radius, which is given to you. Body-centered, as you can see here in this little maybe closer one, has really the same atom in the corners. So it's got the 8 corner pieces, which gives you 1 atom total. Different than the previous one, though, which is why it's called body-centered. Right there in the middle of the body of the cubic cell is a whole atom. So plus 1 more atom gives you 2 total atoms that are happening here. So you have basically a entire atom on the corners, 1 whole intact atom in the center of the cube. And to calculate the radius is 4 divided by the square root, 4 times r divided by the square root of 3 to get the edge length of it. And that's where you can see here, once again, we have our eighth of an atom in each of the corners and 1 whole atom sitting stuck right there in the middle like a ball. And again, that's how we get a total of 2 here for our body-centered. Its coordination number is 8 as it comes in contact with that extra sort of atom there in the center. There's a lot more connection points, and it has a higher coordination number because of that. As you can see here, again, kind of have 1 whole atom stuck in the middle and an eighth of an atom basically on the edges. Lastly, the one that we're going to talk about again is our face-centered. The face centered here has a total of 4 atoms. And the reason for that is, again, just like the other ones, we have a whole atom from the corner there, basically. So we have our 1/8 times 8 corners gives us 1 atom. Different on this is on every face of our cube, we have an atom that's stuck in the middle, which basically means it gets sliced in half. And you have basically a half of atom on each face of the cube. And since there are, I believe, 6 faces on a cube, you got 1/2 times 6 gives you 3 more atoms for a grand total of 4 atoms if you add them together. So this guy has 4 atoms, basically 1 atom on each of the corners of the cube, and a half of atom that's been sliced right in half on each of the faces of the cube to give you 3 more atoms for a total of 4. To calculate the edge runs here, it is 2 times r times the square root of 2. And again, that is going to be used really in our cases to calculate sort of the volume. So what do we use all this for? For a lot of times we'll use this information, for example, to figure out the density of a solid based on how it is in a crystal lattice. Is it face-centered, body-centered, simple cubic, and how it packs in there. So you can use this to sort of figure out the density of an object. And here's that sort of slicing in half I was talking about. So that is your half of atom on each of the faces. And again, there's 6 faces, which gives us 3 atoms, plus the corners, which gives us that additional atom that's present. So let's take a look at an example here and talk about how we can use this information. So for example, we want to calculate the density of aluminum in a face-centered, and it has a radius of 143 picometers. So we're going to look for the density here in grams per cubic centimeters, which is a typical density of a solid, right? And that's equivalent, right, in grams per milliliter. But we're going to look at it in cubic centimeters here since we have sort of measurements that's happening here. So in this particular case, the important pieces of information that's given to us is it is a face-centered cubic cell. So this is a face-centered cubic cell. So if we kind of back up and take a look at our face-centered, which is this last guy that we just looked at, we essentially have a half a cell, a half an atom in each of the faces, and again, a whole atom. So this guy does give us, and the other important part of it is, as we saw here, our radius is 2r times the square root of 2. So we have that sort of information given to us. We know that we have 4 atoms in this case because it is face-centered. We also know that the length of the edge is 2 times r square root of 2. So we're going to use this information to help us figure out the density. So the first thing we're going to start with is the grams part of it. So we basically need to get to grams. So the one thing that we do know is that it is face-centered. So there are 4 atoms. So really, we don't want to overthink this, even though it may look very scary of the question and everything. But what we want to really think about is, I have atoms. How do I get to grams, right? So we should know how to do that. If you have atoms to get to grams, you could use Avogadro's number, right? So you could go from atoms to moles, and then you can use the molar mass to go from moles to grams. So that is how we're going to get sort of the grams part of it from this information. And the important aspect of that is knowing that it is face-centered and it has 4 atoms. So this is really just sort of like an Avogadro sort of calculation here to start with. We got 4 atoms of aluminum. We know if we use Avogadro's number here, that's going to be 6.022 times 10 to the 23 atoms per mole of aluminum. And at this point, we could use the molar mass from the periodic table, which is 2698 per mole of aluminum. So our moles of aluminum cancel, and we will end up with here, looks like 4 times 2698 divided by Avogadro's number. Make sure you use your exponent. That's going to give us a 1.7, if I can read my calculator, 1.792 times 10 to the minus 22 grams. So the first part of sort of figuring out the density is, again, like you can see here, just using the information that is face-centered. Obviously, if this was a simple cubic, it would only have one atom, right? If it was body-centered, it would have two. So that's the importance of knowing, this guy has one atom total, two atoms, or four atoms. Any questions on that? That, by the way, is the top part of what I need for basically the density in this case. The bottom part, which is the volume, is going to come from our volume is equal to our length cubed. And specifically because this is a face-centered, that is how we're going to calculate basically the length of it. And then we could obviously cube it to get to the volume part of it. There is a couple of conversions that you do probably want to do maybe up front. We know eventually we do want to end up in cubic centimeters. And the only sort of length that we have are in picometers. So my recommendation would be to perhaps convert it to centimeters up front, and then you're in the right units at the end. Or at some point, you do need to kind of convert it to probably centimeters. So just to do it up front probably would be easier. So that's what I'm going to do. I'm going to take the radius, which was given to me, and I'm going to convert it into centimeters. So 143 picometers, as was given here. I believe they gave it right there. There is in 1 picometer, 10 to the minus 12 meters. And obviously in 1 meter, there's 100 centimeters, right? So really, I'm just doing this to kind of put my value into the right units so I don't have to remember to do it later. You obviously could do it later, but it's probably just easier to kind of do it up front. And if I punched all that in correctly, I should end up with 1.43 times 10 to the 8 centimeters. Now remember that that is not my length. That is really my radius, or R, right, which was given to us. So that is really this number right here. So we do need to use the length here, which is 2 times R square root of 2. That again is also specific for face centered. Again, if you have a simple cubic or body centered, you would have a different sort of calculation for the length. But again, that is what we do for this guy. So 2 times my 1.43 times 10 to the minus 8 centimeters, and times the square root of 2. So that's going to give me times 2 times the square root of 2. It's going to give me 4.04, call it 5, times 10 to the minus 8 centimeters. Any questions on that there? Now that I actually do have the length, right, I could get the volume by cubing it, because that's going to give me basically centimeters times centimeters times centimeters, which is a cubic centimeter, which is the volume part of it. So my volume will equal the length cubed, and that would be 4.045 times 10 to the minus 8 centimeters, and again, cubed. I'm going to take that number I got there and cube it. And that will give me 6.617 times 10 to the minus 23 cubic centimeters, which is my volume here, right? Any questions on that calculation? Now that we've done that, we could actually calculate the density, which is our mass divided by our volume. So we'll take the mass that we got, 1.792 times 10 to the minus 22 grams, divided by our 6.617 times 10 to the minus 23 cubic centimeters, which is our volume. And we will end up with 2.71 grams per cubic centimeters. It's a long way to go for that, but that is where we are. So that would be the density here of our aluminum as it crystallizes in a face-centered cubic cell. Questions on that calculation? So really, a lot of times in these type of problems, that's what you're asked for, the density. Sometimes you may be given the density, maybe have to work backwards and figure out maybe, you know, what is maybe the radius or something like that, or the length of the cell, kind of working backwards. But most of the time it's this. Any questions on that there? All right, why don't you try one here then? Let's do, that's aluminum, so what we just did. All right, so estimate the density of RB in a BCC or body centered, and it has a radius of 247.5. And RB is 8547 there. Take a look at it. So again, important information given to you in the problem is BCC, which is body centered. Remember, that is the kind of cubic cell where got an entire sort of atom sitting in the middle. And again, you got that other whole atom based in the corners of it. And again, the important information that comes out of that is it has basically 2 atoms total within that unit cell. Also, because it is body centered here, we do need to use this proper thing for the length, which is 4r divided by the square root of 3 in this case. So again, that piece of information gives you really the sort of 2 pieces of information that you need to sort of solve for this. And with that being said, we could really work it the same way. We're going to kind of do our density again in grams per cubic centimeter. And as the little thing here, we could use how many atoms to get to our grams. And again, we're going to use the radius to get to our volume. And using both of those get together will allow us to get to the density. So I'm going to start with our 2 atoms. And again, really just do our sort of Avogadro's number calculation here, as we will need that to go from atoms to grams, basically, first via moles. And obviously from the periodic table, we can see it's 8547 grams per mole. The moles are going to cancel, the atoms will cancel. And again, that's going to leave us with the grams part here, which in this case is 2 times 8547 divided by 6.022 to the 23. Going to get us 2.839 times 10 to the minus 22 grams. That again is, if we think about our density part of it, the mass part or the grams part that we need. Any questions on that there? We are going to use our length here to get to our volume. And again, because these are cubic cells, basically, our volume will be length cubed. Again, I'm going to do the conversion like I did previously, just to get me in the correct units before I kind of go into there. So we'll take our 247.5 picometers. We will use our 10 to the minus 12 meters as a picometer, and 100 centimeters is a meter. Or again, 10 to the minus 2 meters is a centimeter, whichever way you want to do it is fine. 247.5 times 10 to the minus 12 times 100 in my case, gonna give me a lot of zeros, too many to count. Try that, there you go. We'll go with 2.47 times 10 to the minus 8 centimeters. Again, that is equal to our radius, just doing a conversion of the units, not our length. We now can use that into this equation here, where the length is equal to 4 times r divided by the square root of 3. So that's going to be 4 times our 2.47 times 10 to the minus 8 centimeters divided by the square root of 3. And that is going to get us here times 4 divided by a square root of 3. 5.716 times 10 to the minus 8 centimeters. Again, here we do need to convert that into volume. So that is equal to the length, again, not the volume. So we do have to cube that to get us into volume. Just going to erase this here so I got somewhere to write. So to get to our volume, we will take our length we just calculated and cube it. So that's going to give us 5.716 times 10 to the minus 8 centimeters. And again, we're going to cube it. And if we do that there, looks like 1.867 times 10 to the minus 22 cubic centimeters, which is our volume. And now our density is our mass divided by volume. So taking the mass that we got there before, 2839 times 10 to the minus 22 grams divided by 1.867 times 10 to the minus 22 cubic centimeters, I believe. And that is going to give us 1.52 grams per cubic centimeter. Any question on that calculation? So it is pretty straightforward in the sense of calculating density. You just got to kind of keep track of everything. Very common mistakes people make is they convert like their radius into centimeters and think it's the volume, or they put it into the length calculation, then think it's the volume. So again, you guys got to make sure you do all those parts and also cube it at the end. Like I said, variation of the problems, you're given the density, maybe you're asked to calculate something like the edge length of the cell or something like that, kind of working backwards. That type of deal. Any questions on that? So those three you are responsible for: simple cubic, body-centered, face-centered. You should know how many atoms each of those basically contain. Perhaps the length formulas will be given to you, yes, but you should know how many atoms each of those contain, though. Any questions on that there? Good. Hope it ends up it's the same answer. 1.52, not bad. Guess I could continue on. All right, so as we talked about before, we're not going to get too deep into sort of how these solids sort of pack together. But again, there is what is sometimes referred to as packing efficiency. And the idea is to try to get everybody as close as possible, where they have minimized sort of the energy and pack them all into sort of different layers. There's a couple of different ways to sort of pack the layers, and we're not going to go into any of that too much, but you know, there are some different arrangements of how they sort of pack themselves in the three-dimensional space. In an ionic solid, which is sort of crystalline lattice, as we talked about, there is can be described as simple cubic or face-centered. And again, this is the arrangement of something like an ionic solid. As you can see, it's very, very ordered, where they try to keep their distances. And again, they arrange themselves to maximize the attractive forces between positive and negatively charged guys, and obviously minimize those kind of repulsion type forces between similar charges. We know that the smaller guys here are the positive ions, right? The larger guys are the negative ions. Other than the fact that it says it there, we know that because when somebody gains electrons, right, they get larger, right? And when somebody loses electrons, they get smaller, right? So the smaller sort of circle should be obviously the positively charged guys, which have lost some electrons. Okay, so we're gonna go to chapter 10 here, which is solutions. There's a good chunk of this chapter that we've already sort of talked about, and that's like the molarity, mass percent, all those kind of concentration stuff that we did earlier when we talked about titrations and stuff like that. So we'll go back through some of that, but we're gonna kind of go through that little part a little quicker, obviously, because I hope you know molarity and all that kind of stuff at this point. Towards the end of the chapter, we're going to talk about properties of solutions, which are important. And things like boiling point elevation, freezing point, depression, the effect of particles basically floating around in solutions, which are known as colligative properties of solutions. So as we talked about solutions, obviously, a reminder as well, we've talked about the idea, obviously, those are the guys that get the aqueous symbol next to it. There are two parts to a solution. There is the solute, which is the smaller part of the solution. And then there's the solvent, which is the larger part of the solution. Really, the solute is typically the thing that's dissolved in the solvent. And again, as we talked about, I think previously, if you had a sodium chloride solution, sodium chloride is the solute. And obviously, as we've talked about, water is a very good solvent for something that's ionic because of the ion dipole interactions that can occur. So when we talk about liquids and sort of the solubility of liquids, sometimes we don't talk about it as being soluble or insoluble. Sometimes when we're dealing with liquids, we talk about it as being miscible or immiscible. Basically kind of means the same thing. Bless you. If two liquids are miscible in each other, that means basically they're soluble in each other. They're going to mix and everything like that. So if we have two liquids that are completely soluble, they're miscible. And if we have that situation and you put them, say, in a test tube or something like that, and you have two liquids that definitely mix together and they're soluble in each other, when you look at that test tube, it essentially will just look like one liquid in there, right? You won't see different layers or anything like that. It will all mix together. Really remember a mixture is sort of a homogeneous type situation. Solution is a homogeneous situation, and that would mean that it would all look sort of the same in this situation. Example, ethanol and water are soluble in each other. They're miscible in each other. Ethanol looks something like this. So this is what ethanol looks like. And water obviously looks like this. And water, which has more negative on the oxygen, more positive near the hydrogens. This is an organic eye, which is ethanol. And really, this part of ethanol is nonpolar, but it does contain this one bond, which is definitely polar. It has this OH group on it, which is actually what makes it an alcohol. And that OH group, which is polar, type of group that's on there allows it to interact really well with water and be very soluble in it because it can do hydrogen bonding. And as we talked about, a lot of the things that affect the solubility of things in each other is the ability to use the same type of intermolecular forces. So if you're taking two molecules together and you want them to sort of mix, if they are both using really similar types of intermolecular forces, they're going to be very soluble in each other. So water in itself uses hydrogen bonding to basically interact. So when water and something like ethanol come together, they have really no problem interacting with each other through hydrogen bonding. So because they both can use hydrogen bonding here, it makes something like ethanol be very soluble in water because of that ability to hydrogen bond. It does matter in a sense when you talk about something like ethanol, for example, which is very soluble in water. It does matter sort of the nonpolar part of it. So, for example, if you took something that had a lot more carbons than what ethanol has, go one more. And if these are all just hydrogens and carbons, the problem with something like this, which is really long, and now right about now, I'm regretting how many carbons I drew there, but we'll keep going right there. Hydrogens on all of them. There we go. Now we still have this very similar sort of structure to ethanol. It still has this polar part over here, but the difference though is this part of it, the nonpolar part, is quite big. And this nonpolar part of it is really, really big. And it kind of gets in the way of allowing water to sort of get into there and interact well with it. and it actually becomes very insoluble. So something like this, because of the large amount of carbons and nonpolar parts, even though it still technically has that little part that should be able to interact with water, it's really not able to efficiently do that because it's really, really big. And this little part is not going to interact well with water. So when you have something like that, especially something that's organic that has an OH group, when you hit about, I might have mentioned this before, you hit about 5 carbons or so on the back end there where all the carbons are, 5 or more carbons, the solubility really drops to almost nothing because it just gets in the way. And the real reason for that is if you think about anything that is going to dissolve in water, in order to get something to mix with water, dissolve with water, whatever you want to sort of call it there, you basically have to replace water and water interactions with similar sort of solute water interactions. And in the case of something as big as this, it's kind of big and it doesn't interact really well with water, which is a small molecule, and it has no way to really mix really, really well. So that's why we do see solubility drop a lot. Something like ethanol is still relatively small and it has that polar part, so it's able to interact still okay. But as this part of it gets bigger and bigger, the solubility starts to drop and drop. On the other hand, there are molecules that have multiple OHs, and the more OH groups, for example, that you have is going to increase the solubility with water because everywhere there's an OH group, it gives water the ability to interact with it. So, for example, something like sugar, which is a relatively larger molecule, but it has a bunch of OH groups all over it, is very soluble in water because of the presence of the OH groups pretty much all over it, allows it to interact really well with water. So, there are certain things that affect the solubility, and there are certain things that can increase it or decrease it. But overall, when we talk about sort of solubility of things together, we're talking about how these things can interact. And typically, if they are interacting with the same type of intermolecular force, they're going to typically be soluble. If they're trying to use different types of intermolecular forces, they're not going to be so well. When we do have two liquids that do not mix together, they're known as being immiscible. And for example, if you take carbon tetrachloride and water and put it together, it will be immiscible. And if you have a test tube and you put different liquids in that do not mix, what you typically will see is something like this. You will see different layers basically happening here. So you'll see the different layers because they're not going to mix, so they're just going to kind of separate out. And you'll have just different layers of solutions in there, probably separated by density as to the more dense liquid will be on the bottom, the less dense will be towards the top. Carbon tetrachloride, if you don't remember, maybe looks something like this. That is a very symmetrical geometry where everything on the outside is the same, and that means that's a nonpolar molecule. The problem with that is because this is nonpolar, it wants to use dispersion forces. Those are those very weak intermolecular forces that we talked about when we talked about intermolecular forces. Water obviously wants to use hydrogen bonding, which is a very strong intermolecular force. Those are two very different intermolecular forces. So when they get together, there is no way for them to maintain their interaction over the long period of time, which means there's really no way for them to fully mix and stay mixed basically for a long period of time. They will definitely separate out to each other from making different sort of layers. So this brings up a really important idea when we talk about solubility, and you hear it a lot, is the idea of like dissolves like. And really what that means is, again, things with similar intermolecular forces will be very soluble in each other. Things that try to use very different intermolecular forces will be insoluble in each other. That means, in a sense, if you have anything that is ionic and polar, they will be soluble in each other because they can do ion dipole interaction. If you have anything that is polar and polar, will typically be soluble in each other because they could either do dipole-dipole interaction, hydrogen bonding interaction. The one that sometimes people miss is nonpolar things, and nonpolar things are going to be soluble in each other because they both will be using dispersion forces, which means they're going to basically be doing the same type of interaction. You really only kind of cross over into some trouble a lot of times when you try to mix those two and you take something that is polar and non-polar together. That's going to give you something that's going to be insoluble. Again, because for the most part, the non-polar guy is going to be rolling with dispersion forces. The polar guy is going to be trying to do something like hydrogen bonding or dipole-dipole interaction. And again, that's just not going to mix in a sense or work very well. Any questions on that there? So obviously, examples of solubility, any ionic compound is definitely going to be soluble, again, because they could do really a lot of that ion dipole interaction, where basically the positive or the negative ion, for example, if we're dealing with something like water, will work really well with water. The negative side of water, which is the oxygen, will be able to surround that ion. The positive side of water, which is the hydrogen side, would be able to surround the negative ion. That's what again allows these things to dissolve when you take something that's an ionic solid in something like water, and it allows it to basically sort of disappear in a sense into the water metrics. There's also, as we just saw, talked a little bit about things that are non-ionic, so things that are like sugar, which as we know is very soluble in water, and ethanol are really soluble in water. And again, the reason is, as we just talked about earlier, ethanol has that OH group. It's a relatively small molecule, which means it has the ability to hydrogen bond with water, and that's going to allow them to be very, very soluble. If you take something like methanol, which is one carbon, and an OH group, basically. It'll be very soluble in water. Sugar, as I mentioned before, is a little bit larger of a molecule, but what it has going for it is it has a lot of OH groups all over it. And again, sort of the increase in the number of OH groups allows it to be very, very soluble with water because it gives it a lot of points where water can sort of interact with it. And this is what we see here. This is actually methanol. It has only one carbon and some hydrogens. Again, it's small. It has the ability to hydrogen bond with water. It's going to be very, very soluble. We would expect methanol to be miscible with water and look just like one layer if you kind of put it together. There's our ethanol, again, also doing it. Still going to be soluble because of the OH group that is there. And as I mentioned a second ago, if we do make this part of the molecule a lot more larger, we definitely will start to see a decrease in the solubility of it. So when we talk about oil, oil is really just a long chain of carbons and hydrogens. So super, super, super long chain of carbons. I won't draw all the hydrogens, but basically everything is hydrogens there. And when you look at something like oil, because of that, carbon and the carbon bond is definitely nonpolar because they're the same element. The carbon hydrogen bond has a difference of electronegativity of like 0.4, and that is also nonpolar. So water is insoluble in oil is insoluble in water because of that. And again, that is because oil is going to want to use dispersion forces. And water, once again, here is going to want to use hydrogen bonding, super difference in strength and also how it works. And they're not going to be very soluble in each other. What you typically will see is, right, when you have oil and water, the oil will kind of float in the water again because there's no way for it to mix or anything like that. So, as I mentioned before, and essentially for anything to sort of dissolve in something like water, what you have to do is basically replace water and water interactions with similar type of interactions of whatever you're trying to get to dissolve. What that means is typically, for example, something with water, you need something that can kind of do like hydrogen bonding and is not relatively large of a molecule to fit in with all the other water molecules. So that is that like dissolves like, and with oil, that definitely doesn't happen. That also brings us to a couple of aspects of interactions when we talk about how molecules interact and sort of its ability with water. There's sort of interactions which are referred to as being hydrophilic. Hydrophilic means that it is water loving. And those are when you look at a molecule, and a lot of organic molecules are like this. A lot of organic molecules have like a side that is polar, which is very hydrophilic, which likes water. And there's a side that's hydrophobic, which does not like water, which is kind of the non-polar side. So when we look at something like ethanol and we take a look at its sort of structure, it actually does have both of these parts to it. It has a hydrophobic part, which does not like water, and that would be this part here. All the carbons and hydrogens would be the hydrophobic part, and that's the nonpolar part. And over here, where we have the OH group, that would be our hydrophilic, which likes water, which is typically your polar part of it. So having these different regions sometimes within a molecule does affect things like solubility. So just because something like ethanol here, you may look at it and go, it has a lot of carbons and hydrogens, you know, it's that nonpolar part. It shouldn't like water, but it's only a region on it, and it does have that hydrophilic part, which does like water and is able to interact with it. So as long as the hydrophilic part is accessible to water, and the hydrophobic part is not really large or anything like that, you will get a lot of things being soluble in water that has those regions and increases the interaction between water and those molecules. So here, as you can see, this is octane and CCl4. Octane is basically C8H10. It's basically all carbons and hydrogens, definitely nonpolar. And CCl4, as we just talked about, is nonpolar. So obviously, when you mix them together, as you can see there, it just looks like one solution. Basically, everything mixes together and everything looks good. Now, if you take something like gasoline, which again is basically all carbons and hydrogens, definitely nonpolar, and you take something like water, which is polar, there we do get our different layers because again, the top layer is looking for dispersion forces, bottom layer is looking for hydrogen bonding. So what ultimately happens is all the water molecules just hang out together and go, we're just going to continue the hydrogen bond with ourselves, and pretty much our dispersion forces are going to kind of hang out together. Will there be a little bit of interaction at the layer between them? Probably, but again, not going to be able to maintain that, which is again why it sort of separates out. Sort of the idea of the oil and vinegar salad dressing. Again, you can mix it up really good. It will kind of stay mixed, but again, if you put the bottle down, eventually everything will sort of separate out, sort of from each other and stuff like that because they can't maintain that interaction. Any questions on that there? So when one substance is dissolved in another, it's said to be soluble. So salt or any ionic compound is soluble in water. When one substance does not dissolve in another, it is said to be insoluble. There's limits to solubility, and it's usually temperature dependent. A lot of times, solids are temperature dependent. So usually, if you increase the temperature and you're trying to dissolve like a solid in a liquid, a lot of times that's helpful because it does a couple of things. It increases the energy as well, right? So it gives everybody a little bit more energy, and you could usually get a lot more solid to dissolve at a higher temperature than you can at a lower temperature. There's also certain things that are always soluble in one another. Gases are always soluble in one another, and that's just based on the idea that if you have gases in the same container, they're basically flying around, which means they are constantly mixing with one another and they would be soluble in one another. Some liquids are also usually soluble in each other. So that's like polar and polar things, or a nonpolar liquid and a nonpolar liquid would be soluble in one another. Um, again, the idea of that like dissolves like, similar intermolecular force is going to definitely increase the solubility. The solubility of a solute in a solvent depends on temperature. The higher the temperature, the larger solubility of a solid in a liquid. Also, the lower the temperature, you have a larger solubility of a gas in a liquid. That would be for just logically thinking about it. If you have a liquid and you have a gas at a lower temperature, that gas molecule should be moving a lot slower, which means it's going to stay in the liquid part for a lot longer period of time. before it's able to sort of escape. And that means that the gas and the liquid would stay together for a lot longer period of time and stay mixed. That's different than obviously if you had a much higher temperature, your gas molecules is going to shoot right out, of the sort of liquid part because it has a lot more energy and it's not going to take a long time for it to sort of escape. In terms of gases, solubility also depends on pressure. The higher the pressure, the larger the solubility of a gas. And that is because typically at really high pressures or high pressures, we have much smaller volumes, right? So that means that everybody is much closer to one another. And you have a lot more of the gas molecules basically mixing together. Now, when we talk about solutions, there's a couple different ways that we classify solutions. Uh, there is, as I mentioned, a limit to how much you can get to dissolve at a given temperature. If you take something like sugar, pack it like a table and put it into your water, it will most likely dissolve. But if you took like, a Costco-sized sugar container and poured it all into your glass of water at some point, not all of it's going to dissolve, right? So even though some things are soluble in each other, there's always a limit to how much you can get to dissolve at a particular temperature. So what happens if you add too much solute to the solvent? You get what is referred to as a saturated solution. And a saturated solution is basically a solution where you have hit at that particular temperature the maximum amount of solute you can get to dissolve. So you hit at that particular temperature the maximum amount of solid or solute, for example, if you're talking about a solid that you could dissolve in that solution. If you decided you wanted to try to dissolve any more of that solid when you hit a saturated solution, no more of it will dissolve. It basically will just start piling up on the bottom. Will not be able to dissolve anymore because you've already hit that maximum. The opposite of that is what's known as an unsaturated solution. In an unsaturated solution, you haven't hit the maximum amount of solute that will dissolve. So in an unsaturated solution, you could continue to add solid, and you could continue to add solid until you hit a saturated solution. Yeah. So you have an unsaturated solution, you can continue to add solid, it will dissolve, it will dissolve. At some point, you'll hit the saturation point, and you will hit a saturated solution where you pretty much hit exactly the amount that should dissolve at that temperature. And now you have a saturated solution. And then if you continue to put in, it will not dissolve anymore. So you basically could go from an unsaturated solution, continue to dissolve until you hit a saturated solution. And at that point, you definitely have hit the point where no more will dissolve. There's also a third type of solution, which is a supersaturated solution. And a supersaturated solution is a solution where, frankly, in most cases, you have too much solid dissolved in that much solvent. So you at some point got too much of the solid to dissolve into that solvent. And there's a way that you actually can do this, and it's a very common experiment that they used to do years ago. They don't do too much at schools anymore, but you could take something, and one way that you could do it is you could take some solid, say some like sodium acetate, and you could dissolve it as you're heating it up. And this does two things. You're heating it up, which means as you go to dissolve that solid in here, we'll just make like a solution here as it's dissolving. That's going to increase the solubility, right? Because now we have a lot more temperature, which means you can get a lot more of that solid to dissolve in that solvent. So you're able to really like pound in there a lot of solid and get it to dissolve because you've increased the temperature. In addition, also as you're heating it, you're slightly, in terms of the solvent, like water, evaporating off a little bit of it, right? Because you're heating it up, so you're going to lose a little bit of the solvent, but it's going to allow you to get a lot of the solute to dissolve. And after you do that, you make basically a saturated solution in this manner, and then you take it off and you cool it down. And two things happen as you cool it down. Clearly, the beaker gets bigger, but other than that drawing, as it gets cooling down, two things are happening in terms of the solubility. As the temperature comes back down, the solubility of whatever you dissolved in there is now a lot less because it's a lower temperature. But the problem is you've already dissolved it, so it's already dissolved. So as it starts to cool back down and you leave it alone, you don't touch it at all, what will happen is the solubility will start to decrease, but you kind of went past that already. So as it continues to cool back down and cools completely down, you will have now a supersaturated solution because you just basically dissolved way too much solid in that. And by letting it cool back down, it now has way too much solid dissolved in liquid. If you look at the solution at this point, it will look like a solution. It will look like a liquid. It is typically going to be a very, very unstable solution at this point because you have way too much solute dissolved in it. It is so unstable that, and this happens sometimes, that if you just take like the beaker of the solution or whatever it may be, and you just accidentally tap it, it will cause all the solid basically to come out of the solution because it's so unstable because you have way too much dissolved. Normally, what you do when you do this experiment is you take like one super small of a crystal of whatever you dissolved in it, and what you could do is just drop that one little crystal in. And once you hit that one little crystal, it's like, whoa, now that's like way too much. We got way too much trying to dissolve here at this temperature because it's cooled way back down. And what will happen is it will go from the liquid state, and what you will be able to see is actually all of the solid will start to come out of the solution. And it will continue to do that until basically all the solid will come out, and you'll now have like a rock hard solid basically at this point. And that's why I said it's so unstable. I've done this example or demonstration a lot, and sometimes, like I said, just simply like lifting the like flask up and putting it back down, that little kind of vibration is enough to cause all the solid just to come out and stuff like that. Years ago, they used to have students do this like in a test tube and heat it up and put their like thermometer in there. And then when they would make it into the supersaturated solution, it would go solid and be like a popsicle. Their thermometer is like stuck with a solid on it. People are like, "How do you get it out? You break it." No, that's why they don't do it anymore because that's what people would do. They like break their test tubes. But you obviously, if you heat it back up, you could get it to redissolve, right? Because you would change the solubility back to a much higher level, and you could get it back to dissolve. So that's a supersaturated solution. It's a really unstable sort of solution, and this is sort of a picture of that. This is a sodium acetate solution that's supersaturated. It's hard to see, but there's one little drop of it that they put in here, and what you start to see is the solid will basically continue to sort of come out of the solution, and that's what it sort of looks like. You can kind of see it actually coming out until at the very end. This is going to now be like rock hard solid as all the solid basically came out of the solution from where it started over here, where there's basically kind of no solid. You can see this is actually where it hits, and you can start to see the solid come out as soon as it sort of hits. It's sort of like you kind of pushed it way over the line there. You got like way too much of it dissolved. Any questions on a supersaturated solution? All right, let's talk a little bit about pressure and the solubility of gases. External pressure can affect the solubility of gases. This is what's known as Henry's law, also known as like the soda can sort of law, basically, what happens in a soda bottle. Henry's law says that the solubility of a gas in a liquid is proportional to the pressure of the gas over that solution. There's two versions of this. This is concentration, which is like molarity. This is solubility, and it's really molar solubility, which is also molarity. So sometimes books will use C, sometimes books will use S for molar solubility. They're all fancy words for basically molarity in most cases is what they're sort of looking for. K is Henry's constant, and it is a value you could look up on a table based on the solution that you're dealing with. P is the pressure in atmospheres. And you could use this to calculate the concentration you need to have a particular pressure, or if you have a concentration of a solution, what the pressure of the gas would be in the solution. They sometimes refer to this as the soda can thing because when you have a can of soda, you have CO2 bubbles, right, dissolved in the liquid part. And before you pop the top of your soda, there's a lot of pressure, right, in the can. And because of that increased amount of pressure, there's a lot more of the CO2 dissolved in the liquid part of the can, right? And I think I have a better picture maybe here. There it is. This is a table of Henry's laws constants. And again, as you can see, you can look it up based on the gases you're dealing with. But here's the idea. Before you dissolve or pop the cans of soda, you have a lot more of the CO2 dissolved in the liquid part of it because it's under a lot of pressure. When you pop the top, you obviously release the pressure, and that's going to allow the gas molecules now to escape as it's less pressure. In addition to escaping, because you open the top of a can of soda, it has no lid, there's no going back at that point. You're going to have a lot of this CO2, guys, escape the top of your soda. So if you ever open a soda and you see like the fizzing happening, right, that's the CO2 escaping through the top of the can there. And because there's air, this blows that CO2 and gas away from it. And what happens with a soda can if you leave it open for a while and you go back to it? It tastes very flat, right? That's what people say, right? If you ever open up a soda can, come back a little while longer, taste it, doesn't taste as fresh. And that's because all the CO2 obviously escaped the liquid part of it. And also you release the pressure and you lost all that CO2, which made your soda really flat. So that's the idea there of sort of what's happening. And again, before you pop it though, you have a greater proportion of that CO2 sort of molecules dissolved in the liquid part of it. So let's take a look at a calculation here. What is the pressure of CO2 that's required to keep the concentration of CO2 as 0.12 molar in a soda at 25 degrees Celsius? So why don't you give it a go? The KH, the Henry's constant for CO2 is 3.4 times 10 to the minus 2. Calculate it, and again, depending on sort of which one you want to go with, either that or this. And again, they sort of represent the same thing. This, bless you, is really the molarity in each case. We do have the molarity, which is 0.12 molar. Our constant, which again, you would have to look up on a table, molarity in atmospheres, and our pressure. We're going to divide this to the other side, and that will get us something like 3.5 atmospheres. So again, if you think about standard pressure, which is 1 atmosphere, that means our soda can here is about 3 times that of pressure, basically keeping that CO2 dissolved. Any questions on that one there? All right, so just again, some review of some concentration units that we sort of talked about previously. Obviously, in that chapter where we're doing concentrations and stuff like that. A reminder again of percent mass to mass, which is our mass of our solute divided by the mass of our solution times 100%. Remember that as we talked about with this one, the important part of it is the bottom part. You want to make sure that you get both the solute and the solvent together, as again, it is sometimes separated in the questions and stuff like that. This went with the other sort of percent concentration units that we talked about, volume to volume, which is the volume of the solute divided by the volume of the solution times 100%. And we also had percent mass to volume, which is our mass of our solute divided by the volume of solution times 100%. So again, these are 3 sort of percent concentration units that we talked about. First one's kind of grams over grams, milliliters over milliliters, and grams per milliliter. And again, as we also talked about, if you do have the percentage given to you, again, like a 5% mass to mass sodium chloride solution, if you wanted to turn it into a usable conversion factor, that would mean you have 5 grams of sodium chloride and 100 grams of solution, or in 100 grams of solution, you have 5 grams of sodium chloride. So again, these are ways that you can take these percent concentrations and turn them into sort of usable conversion factors. All right, we will lay it up, I think, there for today.